In this chapter, we shall discuss another important topological property called compactness. In elementary real analysis, we have already encountered these topological properties. We already studied that in Euclidean spaces, a subset is compact if and only if it is closed and bounded. But this definition cannot be generalized in the case of arbitrary topological spaces, because the notion of boundedness cannot be defined there. But if we look at the alternative definition of compactness, which says that a subset of Rn is compact if and only if every open cover has a finite subcover, then this definition obviously can be generalized in the arbitrary topological spaces. We will take this as the definition of compactness in arbitrary topological spaces, and we can see that extremely important theorem of real analysis known as extreme value theorem can be generalized for compact topological spaces. Let us go to slide presentation. So, as I told that a topological space X is said to be compact if every open cover of X has a finite subcover. We will consider in arbitrary topological space this as the definition of compactness. So, every closed and bounded subset of Rn is compact. That means every closed interval is an example of compact spaces. Now, as we have seen in various times that only basic open sets serves for us, here is also true that we can say that a topological space X is compact if and only if every basic open cover has a finite subcover. So, it is sufficient for us to consider basic open sets in place of arbitrary open sets. For compactness, much more is true, which is called Alexander subbase theorem. Alexander subbase theorem says that for compactness only subbasic open sets are sufficient. That means Alexander subbase theorem says that a space X is compact if and only if every open cover by subbasic element has a finite subcover. We will prove this in some another module. As in the case of connectedness, when we say that a subset of a topological space X, say capital A, is compact, we always mean with respect to the subspace topology unless otherwise specified. Also, the subset A is compact if and only if every open cover of A by open sets of X has a finite subcover. Now, the following is an example of a compact space. Let us consider the set 1 by n such that n belongs to n union 0, then this is compact. Because this is closed and bounded, so by Bolzano-Vassas theorem this is compact. But if we delete 0 from this set, then this set does not remain closed. So, this fails to be compact. Some examples of compact sets and non-compact sets. The real line R with usual topology is not compact. We already know that this is not bounded. So, by Bolzano-Vastas theorem this is not compact. To get the explicit description, if we consider the open intervals minus n n such that n belongs to the natural number set, then this becomes a open cover of R which has no finite subcover. Similarly, we can prove that the set of rationals with the subspace topology induced from R is not compact. In fact, the open cover minus n to n intersection Q such that n belongs to n has no finite subcover. Similarly, the set of integers z with discrete topology is not compact. The open cover singleton n has no finite subcover. In fact, no infinite discrete space is compact. The open ball Bxr in Rn, that means all y belongs to Rn such that distance of y from x is strictly less than r is not compact. We can also consider the following example. Let P be a polynomial in the real variables x, y. Then the 0 set of P is always closed. However, Z may or may not be compact. For example, if P x y is equal to x square plus y square minus 1, then Z being the unit circle is compact. But if P x y is equal to x, then Z is the whole y axis, which is not compact, because y axis is isomorphic to R and we know that R is not compact. Here by isomorphic I mean that is structure preserving. So, here isomorphism means homeomorphism. We can easily observe that any infinite set with cofinite topology is compact, because in cofinite topology a set is open if its complement is finite. So, if we take any open cover and consider any open set within that open cover, so it misses only finitely many points. So, to cover the whole space we just require finitely many more open sets. That means every open cover has a finite subcover in cofinite topology. So, cofinite topological spaces are always compact. So, this is an important theorem or maybe the main theorem regarding compactness. If f from x to y be a continuous surjection, then if x is compact then y is compact. That means continuous image of compact spaces is compact. To prove this theorem, let us consider x as a compact space and f from x to y be a continuous surjection. So, we have to show that every open cover of y has a finite subcover. Let us consider an open cover of y as script C. Then the collection f inverse g such that G belongs to script C is an open cover of X as f is continuous. Now, since X is compact, only finitely many of them covers X. Say G1, G2, Gk belongs to C such that F inverse G1, F inverse G2 up to F inverse Gk cover X. Then we can prove that G1, G2, Gk cover Y. Hence, every open cover of Y has a finite subcover, that means Y is also compact. Now, let us state some comparison between two different topologies on a space X. Let tau 1 and tau 2 be two topologies on a space X such that tau 1 contains tau 2 and tau 1 is compact, then tau 2 is compact. To prove this, let us consider two topological spaces, one is x tau 1 and another is x tau 2. Now, let us consider an open cover of x tau 2. Since every tau 2 open set is tau 1 open sets, therefore, this is also an open cover of the space x tau 1. Now, since x tau 1 is already compact, therefore, it has a finite subcover. So, this is also a finite subcover of x tau 2, that means x tau 2 is compact. Another result is, if tau 1 contains tau 2 and tau 1 is compact and tau 2 is Hausdorff, then tau 1 is equal to tau 2. To prove this, let us consider a closed set in tau 1. Since tau 1 is compact, therefore, the closed set will be also compact. So, this compact set in Hausdorff's topological space tau 2 will be closed. That means, every closed set of tau 1 topology is also closed in tau 2 topology. Therefore, tau 1 is equal to tau 2. So, these two topologies are same. Next, we shall present another important criteria for compactness in terms of closed sets. Theorem: a space X is compact if and only if any collection of closed sets with finite intersection property has non-empty intersection. So, if we assume this theorem, it will be very easy task to prove that every closed subset of a compact space is compact. In fact, if we take a closed subset of a compact space and now if we take a collection of closed sets in the closed subset with finite intersection property, then this collection of closed sets is also a collection of closed sets in the original space which has the finite intersection property. Now, since the original space has the compactness property, so this collection of closed sets has non-empty intersection in the original space. That means, it has non-empty intersection in the subset which is closed. Hence, closed subset of a compact space is compact. Now, let us come to the proof of the theorem that a space X is compact if and only if any collection of closed sets with finite intersection property has non-empty intersection. So, let us consider script C be a family of subsets of a topological space X. Then according to De Morgan's law, we have X minus union of C such that C belongs to script C is equal to intersection of complements of C such that C belongs to script C. This equality will work for us. By this equality, C is a cover of X if and only if the intersection of the complements of the members of C is empty. Now, the space X is compact if and only if each family of open sets such that no finite subcollection from the family covers X fails to be a cover of X, and this is true if and only if each family of closed sets which possess the finite intersection property has non-empty intersection. This completes the proof. So, we have given the characterization of compactness by open sets, also we have given characterization of compactness by closed sets. Now, we shall see that there exists an intimate relation between separation properties and compactness. We shall see that every compact Hausdorff spaces are normal. We shall also see that compact sets in a Hausdorff space behave like points. Let us go to the slide presentation. As I have already mentioned that compact sets will behave in Hausdorff spaces as points. In fact, in Hausdorff spaces we have observed that every singleton set or every finite sets are closed. Here we shall show that in Hausdorff spaces every compact sets is closed. That means in Hausdorff spaces every compact set behave like points. For the proof, let A be a compact subset of a Hausdorff space X. We want to prove that A is closed. To prove that A is closed, it will be sufficient for us to prove that X minus A is open. So, let us choose a point X in X minus A. Now, for each A belongs to capital A, we can find disjoint neighborhoods UA and VA of X and A respectively. That means there exist disjoint open sets UA and VA where UA contains X and VA contains A. Clearly, the collection VA such that A belongs to A is a cover of A. Now, capital A is compact. So, the collection VA must have a finite subcover. Say the finite subcover be VA1, VA2 up to VAN. And we also consider the corresponding UA1, UA2 up to UAN. Now, take U is equal to intersection of UAI, I runs from 1 to n, and V is equal to union of VAI, I is equal to 1 to n. Then V contains A as VAI such that I belongs to 1 to n is a cover of capital A, and X belongs to capital U. We can prove that U intersection V is also disjoint. Hence, we have that U is a neighborhood of X which is disjoint from A. Thus, X is an interior point of X minus A. This shows that X minus A is open, hence A is closed. This proved that in a Hausdorff space every compact subset is closed. Next, we prove that another important fact that every compact Hausdorff space is normal. To prove this, let us consider X be a compact Hausdorff space and A and B be two disjoint closed subsets. We have to find two disjoint open sets containing A and B. In fact, we shall use the technique of our previous theorem. It is sufficient to prove that X is regular because a regular Lindelof space is normal. Let A be a closed subset of X and X belongs to capital X such that X does not belongs to A. For each A belongs to capital A, let us take disjoint open sets UA containing X and VA containing A. The open sets VA such that A belongs to capital A gives a cover of A, and since A is compact, there is finite number of open sets VA1, VA2 up to Vn which also cover A. Now, let us take V is equal to union of VAI and U is equal to intersection of UAI, I runs from 1 to n. Then U and V will be required open sets for separating X and A. This completes the proof of this theorem. Finally, we prove that in Hausdorff space any two disjoint compact subsets can be separated by disjoint open sets. This can be proved by the application of above two results, and this completes our motto that in Hausdorff spaces every compact set behaves like point. So, in this module we have introduced the notion of compactness for arbitrary topological spaces. We have given the criteria for compactness using both open sets and closed sets. We have also seen that in Hausdorff spaces compact subsets behaves like points. With this we end this module. Let us pass to the another module.